Alright, so in this video I'm going to work a couple of problems. Two of them are going to deal with circular orbits, one of them with a telescope around the Earth, and one of them with more astronomical figures. And the other one that I'm going to do is going to be, the other two problems are going to be dealing with artificial gravity. Okay, I'm going to try to get through these in 10 minutes so I can fit this video on YouTube for you guys. Okay, so the first problem deals with the Hubble Space Telescope orbiting at a height of 598 kilometers above the Earth's surface, and it's asking how fast it needs to be traveling. Now this equation right here comes from originally the Newton's law of gravitation, and in this case gravity is causing the centripetal force, and so the centripetal force is mv squared over r. And Newton's gravitational law says that the force of gravity is equal to g m1 m2 over r and r squared. And so therefore we can simplify, we cancel one of the r's, we cancel one of the m's. Basically we simplify it to be this equation right here, which we're going to use for the next two. The thing to keep in mind is that this mass right here is always the mass that's at the center of the system. Okay, the velocity will give you the velocity of the object that's going around the outside of the orbit. Okay, now this one we're looking at a satellite that's above the Earth, right? I guess that looks more like a TIE fighter than a satellite, but that's okay. So it's above the Earth, 598 kilometers, and then you've got the radius of the Earth, because this r right here has to be from the center of the Earth to the satellite. Okay, so we'll go ahead and plug these numbers in. We can look up most of them. The gravitational constant is 6.67 times 10 to the negative 11th. And then the mass of the Earth we look up to be 5.98 times 10 to the 24th. And that's a 4, not an 11. And then we've got the radius, which is going to be that 598 kilometers, which is 598,000 meters. And then the radius of the Earth is 638,000. And so this is going to be 0008796. And so we can go ahead and put this in, and this should give us the velocity. Okay, so we'll go ahead and do that. We'll say the square root of, I guess it's already given me the parentheses, so 6.67 e to the negative 11th times 5.98 e to the 24 divided by 6978123, and so we get that, and it looks like it took my square root off. So there we go, 7,560. So the velocity is 7,560 meters per second. Okay, we'll go on to the next one. The next one's going to be very similar. This one's looking at a supermassive black hole, but we're still going to use the same equation. It's still going to be the square root of Newton's gravitational constant, universal gravitational constant, times the mass of the big object over r equals v. Now in this one it actually gives us the velocity to be 36,000. The mass of the thing at the center is what we're looking for, right? Because we've got the Hubble Space Telescope finding the black hole at the center of the galaxy. So there's the black hole at the center of the galaxy. Here's the galaxy. We're out here on one of these arms, and we are moving around it with this velocity of 36,000 meters a second, and we estimate that we're about 2.46 times 10 to the 20th meters away from the center. And so we're going to find out how massive that is because of our rotation around it. And so we'll go ahead and we'll have the 6.67 times 10 to the negative 11th. The mass is what we're looking for. The radius is 2.46 times 10 to the 20th. Okay, so first we're going to use the square, get rid of the square root by squaring. So we'll do the 36,000. We'll go ahead and square that. That'll get rid of the square root. Okay, by squaring. And then we'll multiply by the 2.46 times 10 to the 20th. Then we'll divide by the 6.67 times 10 to the negative 11. That should give us our answer, which is 4.78 10 to the 39th. Since everything was in SI, sorry, not 38, 39, everything was in SI units, which means the mass is going to be in kilograms. And yes, that is pretty dang big, but that's why it's called a supermassive black hole. So there you go. There's two problems dealing with orbits, and hopefully those